In quantum mechanics, the Schrödinger equation is a partial differential equation that describes how the quantum state of a quantum system changes with time. It was formulated in late 1925, and published in 1926, by the Austrian physicist Erwin Schrödinger. In classical mechanics, Newton's second law is used to mathematically predict what a given system will do at any time after a known initial condition. In quantum mechanics, the analog of Newton's law is Schrödinger's equation for a quantum system. It is not a simple algebraic equation, but in general a linear partial differential equation, describing the time evolution of the system's wave function. The concept of a wave function is a fundamental postulate of quantum mechanics. Although Schrödinger's equation is often presented as a separate postulate, some authors show that some properties resulting from Schrödinger's equation may be deduced just from symmetry principles alone. For example, the commutation relations. Generally, derivations of the Schrödinger equation demonstrate its mathematical plausibility for describing wave-particle duality. But to date there are no universally accepted derivations of Schrödinger's equation from appropriate axioms. In the Copenhagen interpretation of quantum mechanics, the wave function is the most complete description that can be given of a physical system. Solutions to Schrödinger's equation describe not only molecular, atomic, and subatomic systems, but also macroscopic systems, possibly even the whole universe. The Schrödinger equation, in its most general form, is consistent with both classical mechanics and special relativity. But the original formulation by Schrödinger himself was non-relativistic. The Schrödinger equation is not the only way to make predictions in quantum mechanics. Other formulations can be used, such as Werner Heisenberg's matrix mechanics, and Richard Feynman's path integral formulation. Equation. Time-dependent equation. The form of the Schrödinger equation depends on the physical situation. The most general form is the time-dependent Schrödinger equation, which gives a description of a system evolving with time, where I is the imaginary unit, h is the Planck constant divided by 2 pi. The symbol t indicates a partial derivative with respect to time t. Psi is the wave function of the quantum system, and is the Hamiltonian operator. The most famous example is the non-relativistic Schrödinger equation for a single particle moving in an electric field, where mu is the particle's reduced mass, v is its potential energy, 2 is the Laplacian, and psi is the wave function. In plain language, it means total energy equals kinetic energy plus potential energy. But the terms take unfamiliar forms for reasons explained below. Given the particular differential operators involved, this is a linear partial differential equation. It is also a diffusion equation, but unlike the heat equation, this one is also a wave equation given the imaginary unit present in the transient term. The term Schrödinger equation can refer to both the general equation, or the specific non-relativistic version. The general equation is indeed quite general, used throughout quantum mechanics, for everything from the Dirac equation to quantum field theory, by plugging in various complicated expressions for the Hamiltonian. The specific non-relativistic version is a simplified approximation to reality, which is quite accurate in many situations, but very inaccurate in others. To apply the Schrödinger equation, the Hamiltonian operator is set up for the system, accounting for the kinetic and potential energy of the particles constituting the system, then inserted into the Schrödinger equation. The resulting partial differential equation is solved for the wave function, which contains information about the system. Time-independent equation. The time-independent Schrödinger equation predicts that wave functions can form standing waves, called stationary states. These states are important in their own right, and if the stationary states are classified and understood, then it becomes easier to solve the time-dependent Schrödinger equation for any state. The time-independent Schrödinger equation is the equation describing stationary states. In words, the equation states, when the Hamiltonian operator acts on a certain wave function psi, and the result is proportional to the same wave function psi, then psi is a stationary state, and the proportionality constant, E, is the energy of the state psi. The time-independent Schrödinger equation is discussed further below. In linear algebra terminology, this equation is an eigenvalue equation. As before, the most famous manifestation is the non-relativistic Schrödinger equation for a single particle moving in an electric field, with definitions as above. Implications. The Schrödinger equation and its solutions introduced a breakthrough in thinking about physics. Schrödinger's equation was the first of its type, and solutions led to consequences that were very unusual and unexpected for the time. Total, kinetic, and potential energy. The overall form of the equation is not unusual or unexpected, as it uses the principle of the conservation of energy. The terms of the non-relativistic Schrödinger equation can be interpreted as total energy of the system, equal to the system kinetic energy plus the system potential energy. In this respect, it is just the same as in classical physics. Quantization. The Schrödinger equation predicts that if certain properties of a system are measured, the result may be quantized, meaning that only specific discrete values can occur. One example is energy quantization. The energy of an electron in an atom is always one of the quantized energy levels, a fact discovered via atomic spectroscopy. Another example is quantization of angular momentum. This was an assumption in the earlier Bohr model of the atom, but it is a prediction of the Schrödinger equation. Another result of the Schrödinger equation is that not every measurement gives a quantized result in quantum mechanics. For example, position, momentum, time, and energy can have any value across a continuous range. Measurement and uncertainty. In classical mechanics, a particle has, at every moment, an exact position and an exact momentum. These values change deterministically as the particle moves according to Newton's laws. Under the Copenhagen interpretation of quantum mechanics, particles do not have exactly determined properties, and when they are measured, the result is randomly drawn from a probability distribution. The Schrödinger equation predicts what the probability distributions are, but fundamentally cannot predict the exact result of each measurement. The Heisenberg uncertainty principle is the statement of the inherent measurement uncertainty in quantum mechanics. It states that the more precisely a particle's position is known, the less precisely its momentum is known, and vice versa. The Schrödinger equation describes the evolution of the wave function of a particle. However, even if the wave function is known exactly, the result of a specific measurement on the wave function is uncertain. Quantum tunneling. In classical physics, when a ball is rolled slowly up a large hill, it will come to a stop and roll back, because it doesn't have enough energy to get over the top of the hill to the other side. However, the Schrödinger equation predicts that there is a small probability that the ball will get to the other side of the hill, even if it has too little energy to reach the top. This is called quantum tunneling. It is related to the distribution of energy. Although the ball's assumed position seems to be on one side of the hill, there is a chance of finding it on the other side. Particles as waves. The non-relativistic Schrödinger equation is a type of partial differential equation called a wave equation. Therefore, it is often said particles can exhibit behavior usually attributed to waves. In some modern interpretations, this description is reversed. The quantum state, i.e., wave, is the only genuine physical reality, and under the appropriate conditions it can show features of particle-like behavior. However, Valentini shows that such an interpretation has problems. Valentini points out that whilst it is arguable to associate a physical wave with a single particle, there is still only one Schrödinger wave equation for many particles. He points out, if a physical wave field were associated with a particle, or if a particle were identified with a wave packet, then corresponding to n interacting particles there should be n interacting waves in ordinary three-dimensional space. But according to that is not the case. Instead, there is one wave function in an abstract 3n-dimensional configuration space. The misinterpretation of psi as a physical wave in ordinary space is possible only because the most common applications of quantum mechanics are 2-1 particle states, for which configuration space and ordinary space are isomorphic. Two-slit diffraction is a famous example of the strange behaviors that waves regularly display, that are not intuitively associated with particles. The overlapping waves from the two slits cancel each other out in some locations, and reinforce each other in other locations, causing a complex pattern to emerge. Intuitively, one would not expect this pattern from firing a single particle at the slits, because the particle should pass through one slit or the other, not a complex overlap of both. However, since the Schrödinger equation is a wave equation, a single particle fired through a double slit does show this same pattern. Note: the experiment must be repeated many times for the complex pattern to emerge. Although this is counterintuitive, the prediction is correct. In particular, electron diffraction and neutron diffraction are well understood and widely used in science and engineering. Related to diffraction, particles also display superposition and interference. The superposition property allows the particle to be in a quantum superposition of two or more quantum states at the same time. However, it is noted that a quantum state in QM means the probability that a system will be, for example, at a position x, not that the system will actually be at position x. It does not infer that the particle itself may be in two classical states at once. Indeed, QM is generally unable to assign values for properties prior to measurement at all. Interpretation of the wave function. The Schrödinger equation provides a way to calculate the wave function of a system and how it changes dynamically in time. However, the Schrödinger equation does not directly say what, exactly, the wave function is. Interpretations of quantum mechanics address questions such as what the relation is between the wave function, the underlying reality, and the results of experimental measurements. An important aspect is the relationship between the Schrödinger equation and wave function collapse. In the oldest Copenhagen interpretation, particles follow the Schrödinger equation except during wave function collapse, during which they behave entirely differently. The advent of quantum decoherence theory allowed alternative approaches, wherein the Schrödinger equation is always satisfied, and wave function collapse should be explained as a consequence of the Schrödinger equation. Historical background and development. Following Max Planck's quantization of light, Albert Einstein interpreted Planck's quanta to be photons, particles of light, and proposed that the energy of a photon is proportional to its frequency, one of the first signs of wave-particle duality. Since energy and momentum are related in the same way as frequency and wave number in special relativity, it followed that the momentum p of a photon is inversely proportional to its wavelength lambda, or proportional to its wave number k, where h is Planck's constant. Louis de Broglie hypothesized that this is true for all particles, even particles which have mass such as electrons. He showed that, assuming that the matter waves propagate along with their particle counterparts, electrons form standing waves, meaning that only certain discrete rotational frequencies about the nucleus of an atom are allowed. These quantized orbits correspond to discrete energy levels, and de Broglie reproduced the Bohr model formula for the energy levels. The Bohr model was based on the assumed quantization of angular momentum L. According to de Broglie, the electron is described by a wave, and a whole number of wavelengths must fit along the circumference of the electron's orbit. This approach essentially confined the electron wave in one dimension, along a circular orbit of radius r. In 1921, prior to de Broglie, Arthur C. Lunn at the University of Chicago had used the same argument based on the completion of the relativistic energy momentum 4 vector to derive derive what we now call the de Broglie relation. Unlike de Broglie, Lund went on to formulate the differential equation now known as the Schrödinger equation, and solve for its energy eigenvalues for the hydrogen atom. Unfortunately, the paper was rejected by the Physical Review, as recounted by Carman. Following up on de Broglie's ideas, physicist Peter Debye made an offhand comment that if particles behaved as waves, they should satisfy some sort of wave equation. Inspired by Debye's remark, Schrödinger decided to find a proper three-dimensional wave equation for the electron. He was guided by William R. Hamilton's analogy between mechanics and optics, encoded in the observation that the zero-wavelength limit of optics resembles a mechanical system. The trajectories of light rays become sharp tracks that obey Fermat's principle, an analog of the principle of least action. A modern version of his reasoning is reproduced below. The equation he found is, however, by that time, Arnold Sommerfeld had refined the Bohr model with relativistic corrections. Schrödinger used the relativistic energy-momentum relation to find what is now known as the Klein-Gordon equation in a Coulomb potential. He found the standing waves of this relativistic equation, but the relativistic corrections disagreed with Sommerfeld's formula. Discouraged, he put away his calculations and secluded himself in an isolated mountain cabin in December 1925. While at the cabin, Schrödinger decided that his earlier non-relativistic calculations were novel enough to publish. He decided to leave off the problem of relativistic corrections for the future. Despite the difficulties in solving the differential equation for hydrogen, Schrödinger showed that his non-relativistic version of the wave equation produced the correct spectral energies of hydrogen in a paper published in 1926. In the equation, Schrödinger computed the hydrogen spectral series by treating a hydrogen atom's electron as a wave psi, moving in a potential well V, created by the proton. This computation accurately reproduced the energy levels of the Bohr model. In a paper, Schrödinger himself explained this equation as follows. This 1926 paper was enthusiastically endorsed by Einstein, who saw the matter waves as an intuitive depiction of nature, as opposed to Heisenberg's matrix mechanics, which he considered overly formal. The Schrödinger equation details the behavior of psi but says nothing of its nature. Schrödinger tried to interpret it as a charge density in his fourth paper, but he was unsuccessful. In 1926, just a few days after Schrödinger's fourth and final paper was published, Max Born successfully interpreted psi as the probability amplitude, whose absolute square is equal to probability density. Schrödinger, though, always opposed a statistical or probabilistic approach, with its associated discontinuities, much like Einstein, who believed that quantum mechanics was a statistical approximation to an underlying deterministic theory, and never reconciled with the Copenhagen interpretation. Louis de Broglie in his later years proposed a real-valued wave function connected to the complex wave function by a proportionality constant and developed the de Broglie-Bohm theory.